With no further ado, we're going to go into the panel discussion today. And we have two moderators this time, right? Two is better than one, right? They're both from the School of Mechanical Engineering. I would like to introduce Professor Martin Jian, right, who is a professor in mechanical engineering, and Professor Michael Seeley, who is an associate professor in mechanical engineering, both in this field of advanced and convergent manufacturing. And I think, Martin, you will start out with some opening remarks, and then Michael will speak and introduce our panelists. Here we go. Martin, all yours.
Thank you, Eckhart. Thank you very much for joining this Purdue Engineering Distinguished Panel discussion. I'm honored to serve as one of the moderators for this conversation, alongside with my colleague, Michael Seeley. The future of manufacturing will not be driven by physics alone anymore, or by data science alone. It will be shaped at the intersection. As physics and data and different disciplines converge, resulting innovations will open new frontiers, I think. So in this panel, we bring together a group of distinguished thought leaders who have each contributed significantly to this space. They will share their insights on how hybrid models can address complexity in design and manufacturing, the challenges and breakthroughs in implementing these frameworks at scale, and broader implication for research, education, and so on. So we invite you to listen and engage and think about what lies ahead. Now, I would like to turn it over to my co-moderator, Dr. Michael Seeley, who will help introduce the panelists.
Awesome. Thank you, Martin. So Arvind did a fantastic job of introducing Jen earlier. I will just add that, I met Jen for the first time as an undergrad student in 2008, which means she met me for the first time in 2015 when I started bugging her nonstop for career advice. And it's something where her latest accomplishment was actually riding the hoverboard that you see up here today with no broken bones. So we're sending you back home without falling on the hoverboard. So we're going to count that as a win. But she's been very accomplished in manufacturing, as Arvind mentioned, and it's something where we're very grateful to have her here today. I'll go ahead, since we have limited time, and introduce our other panelists. The next on the monitor here is A.J. Malshi, who's the Eugene and Susie Goodson Distinguished Professor of Mechanical Engineering, and he brings a very unique perspective with his educational background. In case you didn't know, A.J. comes from a physics background, which honestly provides a lot of great and different insight into manufacturing across many different disciplines that he works in, from surface engineering to bio-inspired sustainability to in-space manufacturing. And so that's something that I think is a very unique perspective that we benefit a lot from here at Purdue. And he also is, of course, like Jen, a National Academy member in engineering. He's also part of the National Academy of Inventors. And a fellow as well in SME, ASME, and our International Academy of Production Engineering, known as CIRP. The next speaker we have is Byron Pipes. He knows a thing or two about composites. He's the John Bray Distinguished Professor of Engineering in the schools of Aeronautics and Astronautics, Chemical Engineering, and Materials Engineering. He was also elected to the National Academy at a time where I was wearing diapers, which I think speaks in a lot of ways to the contributions over the decades to his background and what he's done in composites manufacturing, which is quite remarkable. He started the Composites Design and Manufacturing Hub here at Purdue and leads the Indiana Center of Excellence for IACME, which is part of the Manufacturing USA Institute geared towards composites manufacturing. And then last but certainly not least is Ali Shakuri, who joins us as a professor of electrical and computer engineering and is the Associate Dean for Research and Innovation. His area of interest includes things like microelectronics and nanotechnology, specifically around quantum electronics, nano and microscale heat and current transport in semiconductor devices. He led the Wabash Heartland Innovation Network that focused on sensing and digital agriculture and advanced manufacturing. And he's, like the rest of our panelists, have been also very active in commercialization and translation of technology. And so one of the things I want you to get from, how Martin and I organized this panel is that we wanted you to see how this area of hybrid manufacturing touches every facet of engineering, from electrical to mechanical, aerospace, materials. It's something where you're seeing it across multiple length scales, from quantum all the way up to bulk components like Professor Sal was seeing and talking about earlier. And so one of the things we'd like to do next is give each of our panelists an opportunity to introduce themselves, particularly how and what hybrid manufacturing means to you. And so I think maybe starting off, we'll go to Byron and that slide deck to introduce his background in composites, as well as what role hybrid and what hybrid manufacturing means to you.
Thank you. I thought a few slides might be useful to share with you, because some of these concepts, as you've just seen from our extraordinary speaker, it's how complex this really gets to be when you're thinking about all of the details and all of the scales and all the time frames that have to be involved in these processes. I've been thinking about this for a while, but I have to say, my colleague to my right, I've known for quite some time, when she was quite younger, and started working in sheet forming, actually. And it seems to me you were very close to General Motors in those days. And I was at the University of Delaware at that time doing some things in composites. And I was interested in composite sheet forming as a subject, because we were not making parts in that fashion. So someone is controlling those slides. Who's doing it? There it is. I just wanted to remind us what the goals are. And, this whole idea of using machine learning and accelerating physics-based simulations is a really interesting topic, because once you have the physics-based understanding, you know why as opposed to how. And I think that is so important in our future of manufacturing, and I talk all the time about that. Real-time process control, as has been demonstrated here, is going to change our world in such an incredible way. But it will require a lot of new thinking for us engineers, I have to say, and I'm one of you in that sense, that it's really stretching my ability to think about these things. Next slide, please. I wanted to think a little bit about the challenge. We have these great capabilities today, these graphic process units that give us this ultra-fast signal and image processing. It's wonderful. It's not enough. And I guess that's my message. But multi-physics integration through virtual twins is where we're going. But the more physics you put together, the more computational time it takes. And here we've got some real challenges. And I think our speaker showed you some surrogates of where you take the physics and you replace it with something that can be computationally much faster and lead to optimum solutions. We also are in a field where we don't have large clouds of data necessarily. In my mind at least, and this is perhaps not true generally, but large clouds of data usually suggest you don't understand the process, so you're running every possible parameter you can run, and you've now got a library of information for AI systems to examine. But too often, we don't have large data sets in many of these problems, and our sensors are not as good as they need to be. There's lots more that we need to do there. So these are the challenges I see. Now let me take you through one set of ideas that we've developed. And we're 3D printing at scale with carbon fiber and polymer systems. We have some problems that isotropic materials don't have. Our systems have directional dependence. It's a big problem in everything. Heat transfer becomes a huge problem. Everything has 9 coefficients instead of 2 in terms of describing them. Anything from heat transfer to flow phenomena, to melt solidification and shrinkage, to residual deformations, you see the list. All of that is anisotropic in our world. But scale is important. I want to show you what can be done with a physical large scale. Additive 3D is something we've done, a virtual twin for extrusion deposition additive manufacturing. Next slide, please. But along the way, you need to put I think, a structure around all of this. And Boeing's done this pretty well. I've followed a lot of their work, this digital systems model, which includes virtual twins. It's not the only thing there. But what I like about this is it talks about an enduring source of truth for data-driven decisions. That's what engineering is. And we have to now bring that concept of the digital twin into that environment and understand it and use it properly. This is not about geometry. This is about all of the physical processes that we engineers and chemical processes that we engineers have to deal with. So what's a digital twin? Everyone has a definition of this, but it has all the physical as well as the process characteristics of the real thing. Next one, please. So we do 3D printing, and if you ever get a chance to come out to the Indiana Manufacturing Institute, we can show you printing at this scale. We're putting down material at 500 pounds per hour, not grams per minute. These are large things, and therefore all of the processes, though, that are interesting at small scale are also interested in large scale. And so this particular machine, the Thermwood large-scale additive manufacturing machine, is manufactured here in the state of Indiana. But before we had this machine, we built our own. I was very proud of what I saw you doing, altering a machine, building it, pulling it together, building one machine here, altering another one. That's what we engineers do. Next slide, please. So a little bit about this process. As you think about additive manufacturing, there are many things that are happening simultaneously, and many things one has to take consideration. And I'm not going to go through all the details of this, but you certainly need to understand the material, you understand the machine, and then all of the simulation processes that are needed to carry that out. Next slide, please. So we do this in a very interesting way. Here's a shape that we might produce. Next slide, please. It's got a couple of steps in it where we use machine code, a material card, a machine card, if you will, digital material card rather, and we produce residual stresses and deformations. This is pretty interesting because this particular part deformed, let's see, of order 50 millimeters when it across that section. So big deformations coming all from solidification and shrinkage coming from that process. Next slide, please. So now we take this simulation, this virtual twin, and we ask the question, could we print the right shape such that when we're finished, we get the deformed shape to be what we'd like to have? This is what we're always interested in engineering. We want to produce the thing that geometrically and in terms of performance fits the application. Next one, please. That process gives us the post-printing geometry. The shape compensation is done reprinting the part, and you can see here we reprinted this part, and it was accurate within a millimeter in terms of what it could be. This is the kind of thing that virtual twins can do for you so long as they have the physics in them. Next slide, please. So my summary is that these model-based systems engineering are going to accelerate our process of innovation and design. And you've already seen, not coming soon, it's now, AI for intelligent digital twins is here. Most of us are still catching up to it, to be fair. But computational speed is going to have to be through surrogates. We cannot solve heat transfer fast enough. It's one of the many phenomena that is true for. But we will get there. These surrogates will be developed, and we are going to live in interesting times. Thank you very much.
Thank you, Byron. AJ, would you like to introduce what hybrid manufacturing means to you in your field?
So I would like to actually comment on hybrid manufacturing, but I would like to first see why, right? Obviously, you always have a solution, but I would like to first talk about the problem. Because what I early enough, quite a few years before, saw that there are four trends coming together simultaneously. That manufacturing at point of need or a point of service is becoming important. The second trend that I saw is that multi-materials are coming together because for materials and their design would deliver functions. So there is a multifunctionality at the point of need and point of service. The third point is becoming more and more true that we have used to have robot in loop and now we have human in loop with robot. And so there is a hybridization of human robots and data that is happening at the point of need again. And the last but not the least, the supply chains are getting just awfully big. I mean, they're just uncontrollable. So with those four trends simultaneously happening, I will now take this to the space. In why space? Because this was a question years before one of the Army's Future Command asked that where do you see the future of this all going? And I felt like there's a hybridization, and I called it convergence, of four things at the point of need. First is multi-materials, second is multi-processes, adding, subtracting, and phase transforming at the point of need again. The third was the form factors. That form factors and what sometimes you call different design aspects and whatnot, but the form factors of those multi-materials. And the last is atoms and digits or bits or data, if what backplane. So convergence of four things at the point of need in the scenarios to deliver a fully integrated product is why I felt where the trends are and where the hybridization is, and truly that's where the convergence is. So if we can converge human and robots, multi-materials, add, subtract, phase transform materials with form factors and physical digital at point of need. Example of this right now, space commerce, space 2.0 is quite a bit important. Space is a very unique, you talked physics and data driven. So I'm myself grown as a physics all the way through my PhD degree program. I always saw that manufacturing, sciences and engineering, not to make the things, but the science and engineering of making was pretty attractive because physics is hierarchical there. All the way from dislocations at the atomic or planar scale, all the way as you build a large part. So you have going from quantum or nanoscale phenomena all the way hierarchical to the large scale. If I just open this opportunity, because we have still quite many students, how this convergence, what I just described before with the physics, but now take it to the space, which is the third axis to the Earth, if you may call it, that's where you have phenomena like microgravity, where the physics is very different. There's no settling. There are various different surface tension. And there are different physics than here, but space is very remote, very difficult for biology. And we will be making convergence of all these things in space, in orbital or extraterrestrial manufacturing. And why we want to do that? Because we want to be resilient in space operations, supply chains. That's what we are building early enough. So I see, you asked me what I see the hybridization. I see the convergence actually. Hybridization is the way process you get there. Convergence is what you deliver. So one is the input, second is an output in that. But these 4 or 5 things, but now we'll be doing physics on Earth and in space and connecting that through whether it's a digital twin or human in loop. But that's what I see where we are now and where we are heading. But thank you.
Wonderful. Ali, same question to you. What does hybrid mean to you, going from probably the largest scale, referring to space, down to the smallest scale, thinking about now semiconductors?
Thank you for the opportunity. As I was trying to think, there is a lot of discussion about Semiconductor Chips Act and what are some of the challenges to bring semiconductor technology to US. But I thought, since the topic of today's our distinguished guest was how AI can can modify design and manufacturing and how you can make it a closed loop, I thought there is another element of AI that complements, and it's worth thinking about it, and that's related to what sometimes is called 1.5 industrial revolution. You have heard about the first industrial revolution, which was the James Watt's machine, and the second one, of course, is the assembly line. But in between, in 19th century, US became a powerhouse in manufacturing because of one invention here. And that invention has subsidized up till now, and sometimes is called interchangeable machine-made parts. Before that, when you made something, each part had to be paid for that machine, and somebody skilled had to assemble it. The interchangeable kind of machine-made parts allowed US to be much more productive in manufacturing. And as a consequence, we still benefit from this. Tolerance of manufacturing comes in, and meaning that you make a part within certain tolerance. If you want to make something for aeronautics, it's higher tolerance and higher expenses. We had an interesting experience. I'm kind of a novice in manufacturing. I directed the Berk Nano Center for 10 years, and we had an application to make sensors for agriculture and for food, pharmaceutical, cases where you need lots of low-cost parts. And the idea was, okay, printed electronic is an emerging field. Let's print these sensors. It's a simple process. We had some machines set up at the Berk Center. And we had devices that they had the right sensitivity, but the device-to-device variability, just by printing simple layers, were not sufficient for measuring, for example, the nitrate runoff from agriculture. You need a couple of parts per million sensitivity, and the printed part had 20, 30 parts per million sensitivity. So you would say, okay, I tried this manufacturing technique, doesn't have the tolerances. I need to go to a more expensive manufacturing technique, such as evaporation and others. But all of us know that's trade-off between tolerance and the accuracy. At the time, we were working with Jian Cao, one of our colleagues here, and Jian said, what is this variability? Is because when you dry the printed processes, the drying is in ambient air and lots of parameters change. There is no way to physically model that, but he said, let's take an image and let's do analysis of correlations between the response of the part being made and what are the features he could extract from the image. And with some year of working with Bruno Ribeiro, one of our top computer science, he was able to use the image to correct for variability 80% of it. So that's a case that you don't improve the manufacturing and you use some surrogates and only machine learning. There is no way anything physical could have corrected for it. So that was lesson number one, is data give us more flexibility to manufacture things at the scale we need. The second lesson was when we took these devices and put in the field, and based on the best theories that we knew, they should have this ability for us to measure with a couple of parts per million. And what we saw is the difference between day and night, difference between different type of soil and water, was variations of more than 100 parts per million. And says, well, we know that, of course, water doesn't change, so there is other physics involved. So that's another lesson. Physics is always a projection of reality. You need to always add something to it because, okay, there is a diffusion, there is a barrier, wasn't included. And again, we can spend another couple of PhD theses to understand better the physics and how we can model it. At the time, we were working with Ashraf Alam, and what was very popular was this fake news identification quickly. How does some of these websites identify fake news? And interestingly, there are good algorithms that they have developed. And what Ashraf did is, these sensors we make is very cheap, 5 cents each, rather than the $1,000, the commercial one you buy. rather than putting one of them, let's put 5 of them. Each of them will drift because of all the physics that we don't know all of it, but they drift differently. And it's like the fake news, you can actually, by looking at the differences, correct for some of these. And he was able, from a sensor that was drifting by 100 parts per million, obtain accurate results on 3 parts per million over 3 weeks continuously in the field with all the environmental changes. So these 2 lessons tells me with data, we can do much more with manufacturing than we did in the last 200 years.
Thank you. So we talked about the physics-based approaches and data-based approaches and so on, and their innovations are happening, but it needs to be implemented on a real manufacturing floor. And there are still barriers to be implemented at scale. So I'd like to ask the panelists here, what are the biggest barriers to adopt these hybrid approaches or physics-based and AI-based approaches to implement it on real manufacturing floors?
Maybe I would like to start with our guest. So Jian, let's start with you.
Thank you, everyone, for your thoughts. This is, varies from, actually covers a very large range. We are talking about hybrid materials, hybrid systems. We talk about all these different skills. And then you bring in the operation side of the manufacturing, really looking at the manufacturing operation at large scale. So my philosophy is always, if you can solve the problem using the simplest equation, go for that, right? And the reason we do hybridizations is not just because we want to do it. You have to introduce additional functionality or objectives coming to this. And simple material, if you can make it work, go for that. Simple model, go for that. If you think about all these neural networks or all these different things, right? Fundamentally, if you use a linear system, then why do you need to have these fancy, over 1,000 of the neural network to represent that? But the problem is many times we probably don't know what's coming into this, right? The complexity of the system. And then you try to do, see whether you can model it with a fit, surrogate models and the other things. I think the future will be really interesting if you can explain why the surrogate model works. And explaining that rather than just because, we saw those data and that's it, So if we can explain it, I think this will bring lots of knowledge and much more expandable, And that's my thought on that. So when you look at on the factory level, why it doesn't, implement it really fast, it's part of this is because the confidence at the model, right? The confidence at the part. So if you can explain, why these things happen, they have the confidence, because then the machine, if once you implement it, people have the confidence that, it's not going to damage my millions of dollars of a machine and they have one down day, So that's my thought. It's the education, the explaining what's going on.
Ali, would you like to add any more to that? You've been working with companies as well.
Yeah, I think maybe a big part of it has to do also with the resources available. 98% of US manufacturers in number and probably 45% in the number of people employed in manufacturing are in factories with less than 500 employees. And they are part of the supply chain, and they don't have a data analytics group. They don't have even barely an IT group. That's number one. The second is manufacturing is not a field where you change your infrastructure quickly. When we visit local companies in a radius of 50 miles, we have 250 small and large manufacturers. That's an example of what kind of the Rust Belt of the US is. We have many of them that are here since, we have a couple of them 100 years ago, many of them from 50s and 60s, and maybe a handful in 80s and 90s. New ones, maybe 2, 3. So you have a lot of old equipment that they don't have access to data, they don't have sensors, they don't have the luxury, they just upgrade it. Once it's working, rule number one is don't touch it. Interesting thing, one of the factories we visited was actually built in 1980, and they showed us one of their stamping machines, and they said this machine was built in 1950s. I said, but your factory is 1980s. He says, yeah, the previous factory, this was working well. We brought it here, it's still working. This was 2022. So I think that's the challenge. Workforce, not having the knowledge, and the second one, legacy equipment. We have seen outstanding opportunities with machine learning. That is simplifying. Before, you needed to have almost a PhD to run a finite element and do something really useful. With machine learning, maybe the barriers are coming down. The challenge I see is the diversity of manufacturing is that machine learning, for it to work where you need lots of data, and none of the manufacturers, small ones, have lots of data. So then this brings the question of, can you do this in a privacy-preserving fashion, and that's a research.
So if I may make a comment on that, what I have experienced that there is almost a misalignment in the business models of the companies, which connect back to the physics part of that. If you're working with a well-established any equipment manufacturer of XYZ, whatever that product could be, the goal is always manufacturing is a mean for profitability. Manufacturing is a mean for profitability. So you're trying to do everything more with using less. So your margins are better, your bottom line is better, right? That's the driver. Efficiency, efficiency, and efficiency of all type. And I saw that when I was working with two types of businesses in my business life. One was established automotive company, exactly that focus, and they were trying to adopt our product. During exactly same time in the other part of the country, innovative company, automotive company, but their business model was innovation and not selling more cars. They were innovating, going from model S to X to whatever the model could be. And we brought them the physics, and they loved that. They said that this is exactly what we want because we can make better design, better processes, better this, better that. So they saw physics as a tool for innovation for the bottom line, rather than we just want to make more parts and how your product can help us. So I then, in that 5 to 6 months of time period, I almost saw the misalignment that on one company, we were selling physics of the process for innovation as a tool, and their own engineers, this was 2016, were using AI/ML for defect detection on the manufacturing lines. We're the just already established company, we're not interested in AI/ML tool. They thought that this is a very curiosity-driven, completely academic exercise, no interest at all. And this was 2016 time period. So I just saw the misalignment of how industry saw physics as a part of that innovation or bottom line as an efficiency system. Thank you.
So our next question is definitely very relevant for our students here, especially the fact that you've heard each one of our panelists mention the role of data science and how that's changing almost every facet of manufacturing with machine learning and artificial intelligence. And so you should be thinking through, as a student right now, what skills you should be building as a future manufacturer. And so the question to the panelists becomes, well, what role should human expertise play in the future of these hybrid systems that do everything for us? What skills do they need to be developing that would be relevant for a future career in manufacturing that's so data intensive?
My turn. It's an interesting time, students, but it's not just interesting for you as students, it's interesting for all of us. This is a period of rapid transformation. As a matter of fact, one of my colleagues and I are working together to create a composites expert, meaning we're replacing ourselves with something to answer questions that we can answer. And when we first started this idea a few months ago, actually, it was, he had just finished writing a comprehensive book in my field in composite materials. I had written an earlier book in a related, it's composites, but a slightly different part of it. And he took those two books and put them into essentially a AI format, chat GPT kind of format. You can ask it questions, and I was noticing that when he did this, I wanted to test it. So I asked it a question that I knew it was not in his book. I knew his book and I knew my book, and it was in mine, but not his. Well, my book wasn't in yet, so I asked it a question. What was interesting to me was the logic that came out from that discussion. There was no information, but it also occurred to me that ability to pseudo-reason is going to be there. And more than that, these systems have infinite memory. So I wrote that book a few years ago. Honestly, I don't remember what's in it. People might ask me a question I couldn't answer, but that expert system can. It never forgets anything. No, not only that, it integrates lots of things. So as we're thinking about what engineers of the future are going to do, that's the life you better prepare for, and not worry about what's coming tomorrow. But what are you going to do to add value? And as I thought about that, it comes back to the same concept that engineers have always had, which is we know when the answer is right and when it's wrong. That's a very, very powerful capability. And it has to be what we do to add value in the future. Indeed, we're going to have access to information that comes to us from all kinds of sources. If I'm part of society, I will turn to an engineer and say, tell me if that's the correct answer. Is that in the right direction? What's wrong with that expert that's telling me these things that I need to do, you engineers? You know why. You therefore can answer the question, is the answer you're getting a valid answer or not? That's what we do as engineers. When we design airplanes, bridges, circuits, whatever it is, in the end, it needs to work. We need to know why it works and how. And we need to understand the fundamentals of how you question whether it can work or not. Therein lies, I think, the challenge you have for education and what you should focus on in the future. That means you have to have the kind of education we've given you in the past, but you've got to have more in the future. You're going to be competing with an expert system in the future, and you better be better than that expert system or you will be replaced.
Okay, great, thank you. Build on that, if you want to take out your pen and pencil, or maybe just take out your phone. So 2 years ago, I asked ChatGPT this question. So it's a logic question, right? 1 + 1 = 3, 2 + 2 = 15. So keep going. 3 + 3 = 35. What is 4 + 4? Do you get it? 1 + 1 = 3. 2 + 2 = what did I say? 15, right? 3 + 3 is 35. What is 4 + 4? ChatGPT 2 years ago told me it's 21 and give me very logic, a lot of explanation why it was 21. And just before this one, I just want to check it. So I just asked ChatGPT again. It gave me 63. Okay, so things are improving, right? But the explanation is like 3 pages. Instead of you can say it's just, a squared minus 1, So the point that I'm getting is AI is improving. It's really great, that you are competing with AI. And I fully agree that the thing that you need right now is to ask the question why. It's not just about, why, this answer is right or wrong, right? But it's also about why you want to do this way, why you couldn't do the other way. And many times I think when we talk about AI, machine learning, all these things, many times it's also, we talk about data imbalance. So what you see from the textbook or what you see from the papers, all those correct answers. But you learned quite a lot, but actually from those non-correct answers, those failed experiments. So this is what I tell people, coming to our class. If you do just class, why you come over here? Because we learned all these things through our experiments, through our labs. And I'm telling you why it didn't work rather than why it works. And I think that is something, would be very helpful when you think about in the future is asking what question and why.
And I would say what Professor Cao said, there are 2 things I do not believe in the next 50 years, at least that's what I believe AI will do that. One is a common sense. And because AI is driven by data, and data is what you feed, and what you feed is AI yet cannot make a decision it is a good data or not good data. And that is typically driven by common sense because you know the situations. And the second, yet AI cannot predict the accidents. An example of that when the tariffs were applied and I typed in the chat GPT that what I can expect in this situation that tariffs are applied and the US economy and it has plenty of access to all the references. Give me the top 3 scenarios. And the scenarios that I got, none of those scenarios match with where we are today. And so that told me that AI yet cannot predict accidents. So the skills that you should be learning are connected to the data to assess whether it's the right data or wrong data. So up in the hierarchical chain that you can make those decisions. And the second, skills, experience skills to have predictability of disruptions. And that yet AI can't do that. Thank you.
Maybe I want to add a comment. So first of all, what generative AI, ChatGPT, and so on have done in the last 2-3 years is quite amazing. But I think what we should realize is that they do well with explicit language, explicit knowledge, things that is written, things that can be written. And people know that there are things that you know that you cannot write. And those are things that AI can never get it because you cannot write, but humans can. So I think the nature of how people will do things, we will benefit. So I think the best system or the best engineers are the one who take most advantage of the generative AI. But remember, with that, you cannot do innovation because you always do maximum likelihood of what has been done before. Usually innovation comes when you do things that that hasn't been done before. And that was one of the advice my PhD advisor gave. By the way, he just turned out to be 95 yesterday, and he wrote still a single author paper 2 years ago. So there's room for people to be productive. But he made an interesting comment. He got his PhD in 59, 60, And between 60 and 65, he worked on lasers at Bell Labs at the place where all the experts were there and they were inventing lasers. In 65, he went to university to start one of the first laser lab at the university, where there was nobody else who knew lasers. And by 1970, and he has written books and so on, and I was taking his class in 89, he was saying that in the second 5 years, which he didn't have resources and didn't have all the experts, he was much more innovative. And he felt the reason was that experts at the end, they guide you in the common practice of others. When you do things that you have, of course they don't work, but by doing that, you learn things that there is no other way to learn.
That's great. Yeah, we need to make mistakes and learn from it, right? So, given the time, we have 5 minutes. We would like to get questions from the audience. Does anyone have any questions to the panelists here that you would like to ask?
The good news is that they said you have a job in the future, so that you should rejoice in. Any questions?
I guess everything is covered from what we have talked about so
they're
far.
relaxed about their job potential.
Oh, there's one question in the back.
Hi, my name is Albert Patrick, PhD student here. I had a question, I guess, between Dr. Pipes and Dr. Jian. If you would when simulating composites, have you found it would be difficult to manage the computational time when you're adding the additional material properties? And then I guess that would move to Dr. Jian. Would the AI assistants play any role to simulate and reduce the computational time when more variables are introduced?
So the question is, when you do the composite processes, there are so many different parameters out there. And then with the AI, whether they can speed up this, the computational time. So it would not if you just do a brute force, just try to simulate everything equally. I think some of these, certainly you can look at computational methods-wise. You can speed up the single forward analysis, right? But then still, when you have so many different parameters, this is what I think is so-called, I call it mechanistic AI. Basically, you have the mechanistic features you define, and then lots of traditional fluid mechanics has been doing it, non-dimensionalist analysis, right? The physics is there, take that, and that help you reduce the parameters, and then you can do better. So some of those Bayesian adaptive sampling will also be very helpful to tell you where the next point will be. So I think AI too will be very useful for that, because that gives you some of the local sensitivity and you can go for the next one. So the tools are there and more research will be needed for that one.
I'll just say that your point is well taken, and let me give you the example. That part that you saw being printed takes about 6 hours to print. Takes the same amount of time to do the computation of the printing. And the reasonably good, fast computers. So really an interesting challenge that we have before us. If you try the brute force way, and to be fair, those of us with a little bit less creativity have done that, and it is right when it's done, but we can't afford it. So here's the wonderful challenge that you're seeing in examples of how it's done, and we're doing those same things. No, it's not fair to say no one is doing as good a job as you are, in my opinion, but we're studying the same ideas of surrogates and how do you do computations faster. The Russians studied anisotropic systems a lot of years ago. and their application was wood, and that was where this whole thing started with properties that are material direction dependent, at least in this world that I've lived in. Really exciting times. Lots of work to do ahead.
I think we are right on time. Let's thank the panelists again for being here and giving their insights for the topic.